let me pull up some of my Python code. And what's it called? Oh yeah, Game Brain AI. And then, all right, yeah, 11 hours ago when I last was working on this stuff. All right, well that loads up. Just freaking pages of code. I don't know. It's like, I don't know. I don't know if there's a better way to do this, but this is how I code. Let me oh yeah, let me collapse some of these windows because this is ridiculous. All right, so I guess I have some of my data. I don't have to run this because it's in notebooks, but like this is an example of like really noisy data. These spikes are dominating my signal just because that's like when I move my head. So it's so you have to clean that up. Bunch of algorithms I wrote to clean it up. And then, oh yeah, I don't have it. Anyway, I guess this is close. This is an earlier version of what I was working on, but I was trying to extract single trial ERPs from EEG, which is an insanely ambitious thing. So let me educate you guys on what the hell an ERP is. So with EEG, this enterprise resource planning, excellent. EEG. They're called event-related potentials, and this is what cognitive science and neuroscience and the EEG literature uses. Unless you're studying like seizures or something, then you can study like the raw waveforms, which is what doctors used for like decades, up until we got computers. Maybe in the 70s is when this stuff started. So in 1920s, I think, Hans Berger invented EEG, and he's a physician that realized if you put electrodes on your head, you can get an electrical signal. And then when people just look at it with their eyeballs, they see kind of like sinusoidal looking waves, right? You've seen this before. And depending on how like intense these waves are, right? So that kind of thing. Or it could be like this, or it could be like really slow, right? People label this alpha, theta, delta. You've heard these waves before. It's just an indication of how slow or fast these waves are happening. So I'll give you a quick breakdown here. I don't know if any of you, how many of you are in like psychology programs or cognitive science programs, but it's really simple. I mean, delta is the slowest. Often in cognitive neuroscience, we ignore those, but they're about 1 to 4 hertz. This is all from the top of my head, so apologies if I'm slightly off, but whatever. I know what I'm talking about. So there's a lot of variation in these definitions, but theta is 4 to 8, which is studied a lot. I've looked at theta a lot when I did EEG. So like delta is often associated with like REM sleep. Delta starts down. So if you like find somebody who's unconscious and they're dreaming, and you put EEG on the wave, like you'll see these really slow waves, and that's because it just gets stronger when you're sleeping. Theta is like more for concentration, because more dominant if usually it's more in the front of your head. There's some localization there, as versus everywhere on your head. So there's just a lot of none of these things are very clear. Like we try to find what they call correlates, behavioral correlates with these. So often you have somebody do like a task in cognitive science, and then you try to find what in the brain and all the brain signals, what changed. So if you have like 20 people come in and do 2 conditions, one where they're concentrating a lot and one where they weren't concentrating, you might see like much more intense theta waves in the frontal cortex on average across those 20 people between condition. and then we think, okay, theta must have something to do with concentrating, right? It's generated by the prefrontal cortex in the front of the head. It's so this is how cognitive neuroscience increments ahead. And there's like tens of thousands of these papers. All right, so and then there's alpha, which you probably heard of, and that's like 8 to 12 hertz. I mean, the numbers don't really matter, but you could just see that these are increasing frequency. So alpha, which I think I showed on stream maybe a couple streams ago, where I put on my EEG headset and I close my eyes, you'll actually get posterior alpha that you can almost start to see without too much data filtering. So we saw like a spike in the raw noise around 10 hertz. So that's just, this is associated with, I don't know to what extent any of this is interesting, but I'll keep it brief. Alpha is associated with like whenever you're not using your vision, whenever whenever sorry, one of my tabs just, sorry, I was just checking in my volume. Alpha is associated with basically when you have people close their eyes, their alpha gets stronger, and it's the back of their head. So it's associated with like there's probably like a default inhibition on all your visual cortex, and that's about at the alpha range. And so what your brain's actually doing is like letting up some of the inhibition on parts of the brain matter in the back of your head whenever you use parts of it. But it's keeping pretty much everything suppressed, because otherwise all those neurons would be like sending messages upstream to the rest of your brain, and your rest of your brain would just be overwhelmed. So alpha is kind of associated with that, with like sort of inhibition, which is like a natural inhibition that you actually release selectively. I mean, that's actually how brain control works. And then there's beta, and beta is like basically 12 to like up to 30, basically. It gets vaguer here. So beta is associated with motor control. There's actually, they break beta down into low beta, like regular beta, and then high beta, and those are associated with different things. And then there's gamma, and gamma is just like everything that's from 30 up to the rest. And then there's even high gamma, which is often what they are looking at when they're putting electrodes directly on the brain. And that's anywhere from like, I don't know, 80, or there's different definitions, 150 or whatever, and then they go up to like 300 or something. And this is often like 30 to 150 or something like that. And there's different definitions. But so often with like an EEG headset, they don't go past 40 hertz. Oh yeah, so that can still be beta, by the way. So 40 hertz is it gets a little vaguer here, but high beta can be past 40, so it can be up to like 80 or something. But the point is, beta gets looked at a lot over the motor cortex. It's associated with like activity, kind of a flurry of activity. You can see it in the prefrontal cortex too, if somebody's like kind of distressed, or they're thinking a lot, or they're like under a lot of pressure. So it's kind of like that level of activity. There's so much correlates, and to try to generalize them down, that's what everyone's trying to do all the time. But it's not super cut and dry, like the way we abstract out the world, or we like to think about humans, we don't like look at our data and just see that pop out clearly. It's like everything in science, right? Like quantum physics isn't intuitive or doesn't make any sense, because it just doesn't, there's not a great one-to-one correspondence with what we observe and how we'd like for things to work clean and clearly, right? So let me just check something really fast. Let me just check. There we go. All right. Every time I open that tab, it mutes. Okay, cool. Yes, and then gamma's very like localized signal. So if you have a small group of like a focused neuronal cluster working somewhere, and this is what you often have to record with direct electrodes on the brain. So like the stuff Neuralink is working on, There's a bunch of studies that neurosurgeons do in university centers where they put electrode arrays directly on the brain. So there's the skull, and then if you remove the skull, there's dura mater, and if you remove the dura mater, there's the surface of the brain, and they'll often lay electrodes on the surface of the brain. And the reason that doctors are doing that often is to localize where a seizure is happening, because they can't. They're going to go in there and cut out the part of the brain that's like freaking out and causing the entire brain to seize up, because these things spread, and there's often a focal center, and if you cut out the focal center, you can stop people having seizures. And this is after drugs have failed, and this is because the person is like they just can't even live a normal life at all, because they're having these seizures that can be life threatening sometimes, because it can stop you from breathing and stuff like that. So so there's often a lot of data gotten from those patients at university hospitals, because they're laying in the neurosurgical ICU for a few days. And so, a scientist, or if you're like a grad student in a program and you're in one of these science labs, you can come in with your paradigm and you're like, I'm going to show you pictures of dogs and human faces. And then you're like getting this data directly off their brain, and you're trying to see, and so these are kind of things you could be looking at as these are the kind of spectral features, which again, is this idea of like you have these waves. And so delta just means like a 1 hertz wave means the peaks are just 1 second apart, and like a 30 hertz, it just means that there's like 30 peaks in the same 1 second. So it just gets more and more intense. That's all it is. It's just a way to characterize sinusoids. It's not actually that big of a deal. The math gets complicated, but the concepts aren't that bad, especially if you could expose them over and over. So this is one way we can look at brain signal. There's a really interesting phenomena too, that if you collect non-invasive signal, which is what I'm doing with EEG, there's a they call 1/f relationship. So F being on the x-axis, the y-axis being the intensity of the signal. So over here is on this side is delta, which is like 1 hertz, and then over here is like it's like alpha, which you can see over here is like 8 or 12, and then as you go over here, you get up to gamma, whatever the Greek symbol for that is. There's this kind of curve, so you actually get like less intense, and they think this is like a filtering effect, that your skull filters the higher frequency, so we just can't see them as well. It's like pointing our telescopes through the atmosphere, and there's just a certain kind of frequencies that get filtered out. It's a little bit like that. So it's the same thing with electric fields. There's like a diminishing transmission. So often if you're doing like gamma, you can't really see this with EEG because it's so low. It's like at the level of noise. Oh yeah, sorry, that's off the screen. And so if your noise level, in theory, this is theoretical, is at that level, it's kind of below noise level. Also, it means that the way the brain is, let me draw the brain out here. You actually have this like cortical layer, as you guys probably know, right? Which is the entire surface of the brain is a cortical layer, which is a bunch of cells, right? And the entire inside of the brain is just axons, like a highway. It's the connections between all the cells basically sitting at the surface of your brain, and they're all communicating with each other through the middle of your brain, which is the white matter, which is just all these axons that are myelinated, and that's why they're white. And but the outside of your brain is gray because they're all actual cells, neurons, cell bodies. Now, but that's not entirely true, because you have the midbrain and the brainstem, which also has a bunch of neuron bodies, right? So these are really hard to get signal from unless they're transmitting out like delta or something, because delta, as you can see over here, transmits very well, but in order to get like the gamma signatures of deep signals, you have to shove an electrode down there. So I don't know. There's a quick primer, I guess, on some stuff. I kind of an impromptu lecture. So I guess I'm yammering about all this stuff because I'm trying to explain what I've been working on. Uh, I'm trying to. All right. So this is ridiculous because I realized I didn't even explain what ERPs are. But ERPs, let me just clear this out. ERPs are what happens when. Okay. So if you get into like a neuroscience graduate program, and you say you studied psychology, and you're just like, okay, but I really want to know what the brain's doing. So you get into some kind of cognitive science program or um, like neuroscience often is like studying rats or cells. So you have to either get in like a cognitive psychology or cognitive neuroscience or more like a human neuroscience program. But anyway, so that you're studying humans. And but all that spectral stuff I just walked you through also applies to animals too. I mean, they do this stuff on monkeys and rats and stuff like that, but their brains obviously are a little different. Um, but let's say, okay, you studied psychology, you think it's cool, but psychologists have their limits. After a while, they're just kind of rambling about their own experiences as a human, and they might do some surveys or they might have people do some tests, but they're kind of solipsistic philosophers is kind of what I call them. Solipsistic meaning very self-centered, like they think that their self is the universe kind of thing. And you're like, okay, but I want to know how the brain works. So you get into a program, and your PI is super cool, and they're like, oh yeah, go do experiments right away in your first semester or whatever. So what they do often, oh, it's off the screen. Okay. What they do often is you have a paradigm, which you might be aware of this. You sit somebody in front of it. You put their head in the headrest, right? You have their eyeballs looking at the screen, and you present something, and so you have to create a very reduced, controlled environment so that you can see. Because if you just have somebody like go to the store with EEG equipment on and lay down on their cell phone and read, and you see differences, you have no idea what those differences are due to. Is it because they were in a public setting? Is it because they were on their feet? Is it because they were outside around other people and when they're at home on their sofa, they're alone? Like, you don't know you can't correlate the behavior with the neural signal, so you don't know why the brain's reacting the way it is, because there's too many factors. So that's why these experiments get so dull, right? Anyway, the point is what they do is they do something like, so let's just stick with something like human faces versus places. That's the often thing. Faces versus places. They often do that one. So like, they'll show you a bunch of houses, and then they'll show you a bunch of faces, and then they're just like, oh, how does the brain react? And then you like, oh, okay, there's like a face, like a human face center in your brain that seems to be reactive to faces, and it's really good at discriminating human faces and stuff like that. It's like a dedicated area, which has been disputed a little bit, but whatever. The point is, you have to show them like maybe 100 human faces, and what you do is you're recording brain signal from their head, and then you end up time locking it. So this is 0. This is about let me move this over. It's about 500 milliseconds. This is about 1,000 milliseconds, which is, I'm so sorry, 1,000 milliseconds, which is 1 second, right? And so what happens is you say you're collecting from a certain electrode. What they eventually want to get is something like this, which is called an ERP, and it's just this characteristic, consistent way your brain responds to stimuli, laboratory stimuli at least. Because in the real world, your eyes are just jumping all over, and these ERPs are probably getting smeared together, and you can't see them. So that's why you have people sit in a dark room. You have them look straight ahead. They're not moving their eyes around. Their heads in a thing. They're not like clenching their jaw. They're all these things that give off noise, and they're looking straight ahead. And they're trying. And you're telling them not to blink. When the task is going on, or minimize their blinking. And later you find out which trials they blinked on, and you throw them away. And you get like 100 trials on them, and you get like 100 of the faces and 100 of the houses, and you get this kind of wave. And this is called the P100 because it happens at 100 milliseconds. This is called an N200. We won't go through all this, but I'm just telling you that there's this like, it's like an EKG, right, for the brain. The EKG has this very characteristic, has this signal. This is the P, this is the QRS complex, and this is the T. And we know where these are coming off of in the heart. This is atrial, this is ventricular, and this is like a refractory. And so there's a bunch of things as like a doctor, you get trained on read EKGs. Like if this distance increases, you know that's because there's like, for instance, this one is the simplest one because this is atria and this is ventricular. So literally when this distance increases, you know that there's a AV node problem as a doctor. That's what you do. You learn how to read EKGs, and there's a few things like this you learn how to figure out. So you get a whole strip of them where this you see a bunch of them, and then you keep looking at all of them. And you see this consistent distancing. You're like, oh, there's an AV node problem, which just means there's an electrical conduction problem between, say this is the heart really fast. These are the atria, right, and this is the ventricle. The signal kind of starts here, spreads throughout the atria, and then it collates right in this node, and then it re-spreads out to the ventricles. But this is like almost like an electrical system, and there could be a problem there sometimes. So you can see this with the EKG, and so the EKG is a very characteristic thing. If you ever had EKG done, or you kind of wear your Apple Watch or something like that, that's what they're using. The brain's got a similar thing. It's like the EKG for the brain. I guess that's a good way to explain it. And so it's called an ERP, and it's event-related potential, which means if I stick you in a room, have a dark headset, have you stare at a black screen, and then things pop up and then they go away, I can see how your brain responds. So the point is that then in a face versus place, let's stick to our simple experiment. If we're looking at a certain electrode, like say over a certain part of the parietal area where we know that it's the fusiform complex, the FFA, doesn't matter, just a part of the parietal center that processes faces, that like it's all about human face processing, more or less. I mean, again, it's all, everything's conflated in the literature, but what you'll see is something like a very strong ERP for the if you take all 50 or 100 faces of that person, and then if you take all the places, I'm just going to draw a house, you're going to see a much weaker one, something like that. Sorry, you can't, it's off the screen. So you might see, like, for instance, you might see the same P1, the same P1, but you'll see like a diminished N2. So I'm just going to draw it here with a different color. And we're almost done with this. I apologize. Same P1, but then the N2 is just a lot weaker, and maybe even the P300 is weaker too. I don't know. And then they'll note that, and those are part of the correlates, right? And then from like thousands of papers, we know that the N2 deals with roughly object recognition in the brain. So I guess we could walk through this kind of, I don't know. Well, whatever. Let me put that on hold for a second. But I just want to finish this concept. So that's why, and I'm just going to draw it here in case my enunciation isn't as good and you guys can't. I'm saying ERP, event-related potential, if you want to look this up later. But that's what, so my whole thing, this has been a big like like mission of mine, I guess, is that there's no tools, there's no like consumer tools to get an ERP. Like there's actually EKG tools now, like at least for atrial fibrillation, which is one heart condition, you could put your Apple Watch on, and your Apple Watch can actually tell you if you have atrial fib, which is insanely cool to me as somebody who was in medicine like whatever years ago, and I'm like, why don't we have this for the brain? A bunch of people are interested in the brain. We could get this kind of thing. Like this is an example where they're contrasting two ERPs here, and there you can see a difference there. It's hard because it'd probably be overwhelming to like interpret all this. I mean, if you just give people raw tools, but we have like no way to do this, and partly is because the way thousands of science studies are done is in these insanely controlled conditions. So nobody's even trying to push this towards like, can we take an EKG while you're running, which is basically what the Apple Watch does. I mean, you have to actually put your finger on the thing. You actually have to sit down. I'm confusing it with the heart rate. So at least heart rate monitors. Heart rate monitors are a good example. Heart rate monitors, they record all the time. It's very cool. I'm sitting at my desk. It knows I'm sitting at my desk because I'm not like the way I move my arms around with the inertial accelerometer. It can tell that I'm not like walking around. And then I have this elevated heart rate for a long time, and it's like, oh, you're getting stressed out, but you're not moving. That's bad. You should go take a walk, which is the ultimate in sort of like technology helping give us awareness. And I think it's really cool if we can use technology to give us awareness, because it sort of like lets your brain focus on other things, you know, because you have technology watching these things for you. Anyway, so one of my like, I guess, missions was, and you know, this kind of, I wrote a couple grants a year ago, and I started working on this stuff. I told you, I think in my AMA, I was just super bored at my job, and I bought a bunch of hardware, which I'll show you in a bit. And I've shown you before. Built an EEG headset, built an eye tracker. I didn't have any hardware expertise at all. And I barely knew any Python, but I've just been teaching myself all this stuff because I'm like, I understand all this stuff, you know, this stuff that I'm showing you, but this is only useful in the laboratory environment. It's like this esoteric, you know, it's like it's sort of, I mean, it is a science, but it's kind of tragic, right? It's like literature for literature's sake. You know, it's like what are you going to do with it? It's even worse than, it's like I don't know. I don't want to crap on anybody's field, but those fields where like the only thing you can do is go teach the next generation it. You can't really do anything useful with it. And that's kind of what this stuff felt like after a while. I'm like, you know, why did I learn all this stuff? Why did I spend all this time getting a PhD in it stuff? Because ultimately what I had to do to make money is teach myself machine learning and go get a job in machine learning and just kind of ignore all the neuroscience stuff. But I learned all this stuff because I was interested, because I was like, how does the brain work, you know? And it occurred to me that there's like no way for you at home or me at home to see like what my brain EKG, if you will, or brain signals look like when I'm doing different things. Like I want to play an action FPS game. Now I want to play a strategy game. You know, what happens to my P1? What happens to my N2? What happens to my P300? And then I can go in the literature and see what all these things mean, roughly as best as we can tell. Like the EKG example, where we know there's an electrical conduction issue with the AV node, if you remember me rambling about that. So I started thinking about how can you build something like this, because laboratory EEG equipment costs basically 50 grand. You know, they're getting a little better now. There's like, but if you use like Biosemi or the big companies in the world, all the university laboratories buy from like Biosemi or Brain Products, it's 50 grand easily, because, you know, they'll say, oh, it's only 20 grand for the electrodes, and then you have to buy the amplifier, and then you have to buy the caps, and then you have to buy replacement parts, and then you have to buy their proprietary software, which only works with their hardware. You know, it easily ends up being 50 grand. Then you have to have a maintenance contract or warranty, and it's ridiculous. There's no way like you or I could just, you know, it's like seeing your heart rate, right? You just want to see your brain heart rate or your brain EKG. And then the other thing I realized too was that, and I actually saw finally an article literally yesterday from a German lab that did this. But I've always wondered why, instead of, gets a little maybe too technical for you guys, but I don't think so. I mean, you'll understand. If you don't understand, it's because I'm explaining it bad. It's not because it's that complicated. But the idea is that if you're stim locking, which is locking it to the stimulus, so like I said, you're presenting a face. Oh, wow, it's off the screen. Sorry, guys. If you're stimulocking and you present a face, and then you present another face, and then you present a house or whatever, you know, and then what you're doing is you're taking exactly when those occurred and you're lining them all up at zero, and then you're averaging them. So not only do you have to do a bunch of signal cleaning, okay, there's a lot of problems with this stuff, but one problem is that you have them in a laboratory environment and you have to stim lock all of them, right? But my thought was, why can't we eyeball lock it so that if I'm in like a real world environment, I'm not in a laboratory with my head in a chin rest and there's this arbitrary stimulus on a computer screen, but I'm like at my computer like I am right now, and I want to play games, and I'm like engaging with something, and then I'm looking over and make sure like the chat stuff's working, and I'm looking, and then I'm talking to somebody, and like we should be able to get environmental or ecologically valid, as they like saying, environmentally usable stim locking. And so my thought is that we just use, and that's why I have an eyeball tracker. I built an eyeball tracker because eyeball trackers, as it turns out, also cost like 20 to 50 grand. By the way, they're ridiculous. The only the biggest eye tracking company in the world, called Tobii, which I got quotes from them like a year and a half ago. All 30 grand easy. I mean, if you want to get anything decent, they have some glasses version, which are still expensive as hell, but they're cheaper, like 10 grand. They're not high frequency enough they're just kind of seeing in general where your eyes are lingering. But that's not what I want to see. I want to see, because in order to get these EKGs, you have to really stim lock it very precisely. If you have like a, say, 100 millisecond jitter, meaning the accuracy is accurate within like a tenth of a second, that's not good, because just imagine we start averaging one trial like that and we average another trial like that. It's this blurring effect, right? And you're not going to see anything. When you add all that up, you're just going to kind of get something like that. So you have to have pretty decent eye tracking. But the reason eye tracking is important, to get back to my point, is that, and I've tried to explain this before on stream, is that one way we do, the way everybody does in laboratories right now, is they present something on a screen, right? And then they see what that timing is, and then they go to a black screen, and then they present something else. But what's really just happening is it's hitting your eyeball, it's hitting the back of your brain. Well, what naturally happens if you're not in a laboratory is that your eyes are just jumping around, and every time your eyes jump around, there's sort of a new image being projected on the back of your brain. Anyway, whatever. That's my best attempt. We can try to tackle that later. But eye tracking good, because you can try to start getting a stim lock thing. Anyway, so then I built my own eye tracker, built my own EEG headset. Still cost me a couple grand, but I was working. I don't really spend money on much else. I did it, applied to a grant, got some money, thank God. So I recuperated my costs, and I've been working on this, on and off, because I do work full time, and sometimes I like to do other things. But anyway, so this is what I've been working on. So this is what I've been working on the last couple of weeks, actually the code, which has been a freaking nightmare, but I got it working. So these are single trial ERPs. So that's another problem, is that often you have to average 50 or 100 trials, on top of which most studies are averaged across participant too. So they'll have like 20 participants come in, each one do 50 or 100 trials, and then you get these clean ERPs. I've done studies before, and they're not very clean at the individual level, even once you've averaged like 50 trials together. So I'm trying to get single trial ERPs. So I don't know. I think these are pretty friggin' good, because what I'm ultimately going to probably do is like average like 5 or 10 of them together to get something more robust. But the idea is if this is the stim, if that's the stim, you can see like a P100, P300, that kind of thing. It's a little probably esoteric for you guys, but yeah, that's what I've been working on. So the point is, I want to get. So there's no technological solution in the world that exists for this right now at all, which is ERP measures or stim lock measures, if that makes any sense. Most people just look at like theta or alpha from like the last minute, and then they just tell you that, and that's it. But for me to make any sort of progress in this stuff, for people to actually have like usable neurotech, I think this is what we have to do. So this is what I've been working on. So I got something working. It's really cool. I wrote a bunch of custom denoising algorithms. I combined the EEG and eye tracking to do this, generate ERPs. So at some point I'll show you guys that. Um, I got it working last night. The problem is I ripped out the wire, so I have to fix the wire first. So I don't know whether to fix the wire on stream or just fix it later. But it's a really small thing. It's just part of my, yeah, this wire got ripped out. So I don't know. I might just fix that and then run it. Um, I don't know. So it's always hard to know how interesting this stuff is. Um, but yeah, I do want to show you that. So either this stream or I'll stream again really soon, and I'll just show you the thing. So I was getting like live ERPs, which I think is really cool. And then the next step, because this is, so I went from raw EEG to like cleaned up signal processed EEG to remove all the artifacts that happen. Then from that to ERPs, and we're still not like in interpretable land. Like if you guys, like I think it's super cool I got ERPs, but you guys are gonna be like, who cares? What the hell? It's because I gotta like interpret what all these things mean. You know, I kind of have to like, it's not enough to have an EKG. Like going back to my EKG metaphor. Like you have to have like AI or something interpret, not only automatically detect that there's an increased difference compared to average, but then say what that means. It's like, oh, there's an AV node problem, and then what does that mean in like layperson language, which is like there's an electrical problem with your heart. I don't know how to make it into layperson language, but that's what I have to do. So I have to work on that. But I think a lot of the technical challenges of it is actually pretty. Actually, I've completed most of the technical challenges of it, which I'm really happy about. Anyway, just letting you know what I've been up to, why I've been gone for like 2.5 weeks. Because I've been on a wacko sleep schedule working on this stuff. But yeah, I finally got it to work, so I'm happy. So hopefully down the road, what I'm going to do is like I said, I'll probably show off the ERPs. Then I'll make them more interpretable, like what it means. Like, are you accessing memory currently? Are you paying attention? Like, are you deploying visual attention versus attention like inwards? I think that kind of stuff might be more interesting because it's, you know, in terms of the relevance to people, how flexible is your brain? Like, how much are you switching mindsets or task switching? And then as you're playing a game or something like that, and you're like locked in, and you're, you know, like how we all have this problem, right? When you start playing a game early on, or even, you know, and you're not like paying attention to stuff because you're just kind of locked in, you could have something just tell you like, you know, and then I can add like even a vocal thing to it that like lets you know. Yeah, I don't know, whatever. It's kind of just a side project at this point, but it's kind of an intense side project. So that's what I've been up to. Yeah, I'm just gonna put this away because I think it's a lot of intense science for today. I did start